Hello, everyone, and welcome to the third and final part of my talk on Cayley vibrations in the Bryan and Salomon manifolds. In this video, as you can see, I will discuss the construction of Cayley vibrations in the Bryan and Salomon manifolds. So let me first recall at which point of the story we are at. So we have the Bryan and Salomon manifolds, and these are just spin 7 manifolds with full holonomy spin 7, and are very explicit, so we can work on them. On this manifold, we would like to apply a cohomogeneity 1 method. So we want to find subgroups of the automorphism group with three-dimensional orbits, and so we've done that in the last video. And for each of these subgroups, we try to construct a Cayley vibration in this talk. So we can very easily split our video into many blocks, and each block is going to be essentially the study of one of the actions that we consider. The first case, which is the easiest one, is when our subgroup is the identity on sp2 times sp1. So this action on the negative spinor bundle of S4 is trivial on the basis and is the usual sp1 action on H on the fibers. So the fibers of the usual projection are invariant under this action, and as seen in the last lection, there are also Cayley submanifolds. By uniqueness of Cayleys, we deduce the following proposition. So the usual projection map pi of S4, defined from the negative spinor bundle of S4 to S4, makes the Bryan and Salomon manifold smooth Cayley vibrations invariant under the action of G. Obviously, the fibers are just smooth R4s. So in particular, the natural Cayley vibration structure of the Bryan and Salomon manifold is a special case of the vibrations that were constructed with other Gs. So the second case is when G is considered to be the lift of the action of S03 times the identity. So the lift of this group acting on R5 times the identity on SP1. So given G, such a G, we have the following theorem, which is going to be much clearer from the last slide of this block. So the theorem goes as follows. So each Bryan and Salomon manifold admits a G-invariant Cayley vibration, and the parametrizing set is S4, and the fibers are of topology R4, F3 times R, or the OCP1 of -1. Now the fibers are smooth apart from an S2 times S1 in S4. So in particular, the smoothness is preserved apart from these S2 times S1. Now the singular Cayleys can only have topology R4s and separate the two remaining topological behavior. So these Cayleys of topology R4s are kind of a wall between the topological cylinders and the topological bundles. At each point of the zero section of the negative spinor bundle of S4, we have infinitely many Cayleys intersecting. So what is the idea? The idea is to choose a nice frame for the negative spinor bundle, which is compatible with a group action and that diagonalizes G, the metric. The reason is because we want to use tau, so the omega true valued 4,4. And we want to have this tau in an easy enough form so that the relative ODEs that we get are going to be fully integrable. So let's start by choosing the coordinates and so the frame for our action. So we parameterize S4 contained in R5 by splitting R5 as a copy of R3 plus a copy of R2. This is because this is clear by this action here. So an element of S4 is going to be written as cos alpha U plus sin alpha V. Well, not plus, but comma sin alpha V, where U is an element of S2, which we parameterize in spherical coordinates, and V is just an element of a circle. So on the fibers parameterized by A0, A1, A2, A3, we define A0 equal to S cosine of delta minus gamma half, A1 is S times sine of delta minus gamma half, and A2 is equal to T cosine of delta plus gamma half, and A3 is equal to T times sine of delta plus gamma half. Well, the reason is that if we fix a point in the basis, gamma parameterizes the orbit in the fiber. Note that this is essentially a kind of up vibration type of map. Indeed, if instead of S and T we put some cosine of Xi and sine of Xi, we use precisely the up vibration map. But what it is very interesting is that with this parameterization, the orbits are just given by theta, phi, and gamma. So now, if we assume that the coordinates not parameterizing the orbits, so essentially we're looking at the space of orbits. If we assume that these coordinates depend on a parameter Xi, then the tangent space of sp1 invariant Cayley's is spanned by d theta, d phi, d gamma, and s dot partial s plus t dot partial t plus alpha dot partial a alpha plus beta dot partial beta plus d dot delta dot partial delta. So what does it mean? It means that so in the space of orbits, we consider a curve, and this is the tangent space of the curve. So each point of this curve corresponds to an element of the orbit, so an sp1. Now the Cayley condition for the sp1 invariant submanifold becomes the system of ODEs. So beta dot equal to 0, ts dot minus st dot equal to 0, delta naught equal to 0, and this ugly equation equal to 0. So the first three terms are very easy and very understandable. Indeed, if we define u as s times t and v as s over t, the solution of the ODEs are given by the following first integrals. So beta, delta, and v are, well, obvious by the first three equations of the system, and f is the only one where you have to do just a little bit of work. So the level set of F in the space given by alpha and U is this one. So let me just spend a few minutes to describe what's going on in this space. So we are fixing beta, delta, and V. And each point of this plane, this piece of plane, corresponds to an SP1. So we have SP1, SP1, SP1. We have this family of SP1 living in our space. Now let's, and the level sets of F correspond to the solution of an ODE, because beta, delta, and V are fixed, and the level set of F is going to give us a solution of the ODE. So in particular, we can deduce the topology of our vibration of our Cayley, SP1 invariant Cayley, by looking at this picture here. So what's going on? So we have SP1 at each point here, and this SP1 is going to 0, so U equal to 0, so to a 0 section. And at the 0 section here, our action is not SP2 and it is not three-dimensional anymore, because it works like an SO3 acting on on R3, so it's an S2, and by topological reasons, this line is topologically OCP1 of -1. Now let's consider the black curve instead. So we have each point corresponds to an SP1 apart from when we meet the 0 section. So when we meet the 0 section, we are at the point where alpha is equal to pi half. Now, alpha equal to pi half means that we are in 0 times R2. So the point is fixed by the action. So we deduce that the topology of a black line is an R4. Finally, the topology of the red line is clearly a S3 times R. So by working out the beta, delta, and V, we can also deduce that the parametrizing space is topologically an S4, that the singular fibers are S2 times S1, but it shouldn't be that surprising because, well, beta is the S1 and delta and V are going to give us an S2 by the op vibration argument. Now, the only thing that we are left to check in order to prove our theorem at the beginning of this section is the smoothness. And in order to do so, you can linearize your problem near the points of the boundary of your patch and see what's going on there. I just by blow-up analysis, you can see that this is the only point where we have singular fibers. So the last case that we need to consider is the lift of the SP1 times identity action. So in this case, analogously to the SO3 times identity case, we have the following theorem. So on each Brownian Salomon manifold, we have a G-invariant Cayley vibration. So the parameterizing space is once again S4, and the fibers are smooth cylinders or planes, and a single S4, which is the zero section. So the reason of this S4 is just by looking at the action. Indeed, if we look at the action, we have SP1 times the density, and when we restrict to the zero section, this SP1 has a three-dimensional orbit, so it needs to be the whole S4. Now, finally, there is only one point which belongs to the zero section where multiple Cayleys can intersect. And these are the Cayleys of topology R4 and S4. The idea is to choose as exactly as in the other case, is to choose a frame for the negative spinor bundle of S4, which is compatible with group action, and that is going to give us easy ODEs. In this case, unfortunately, the system cannot be fully integrated, but we will get just a single ODE to study, and we do that via a dynamical system argument. So, analogously to the argument for S3 times CD2, we see S4 as a family of S3s. So we have a family of S3s that are shrinking to a point and at pi half and shrinking to a point at minus pi half. So by essentially doing the same analysis as the one done for S3 times the identity, we get the Cayley condition for SP1, SP1 invariant submanifolds, Cayley submanifolds, is the proportionality of the Econise and the following ODE, which is given by this line here, is the ODE that we need to satisfy. So by a dynamical system argument, so writing, let me use the pen, the A0 dot over the C times the C over the alpha dot, we get the A0 dot over the alpha. Well, the dot shouldn't be there. This is equal to some function of alpha and r, and we study with the sign of that function, and we deduce that this is the graph that we have to get. Now, as in the previous case, let's look briefly at the topology, and the rest is immediate. So in red, the topology is once again S3 times R. Now in green, we have a family of spheres, of SP1s, that are shrinking to a point, but this point is minus pi half and 0 at the zero section. So we are here, and the orbit is just one point, and so we get our force. So these are just topologically planes, topologically are fours, and in a similar manner, one can deduce that also these are topologically are fours as well. So the last case that one should try to do is the SO3 acting irreducibly on R5, sorry. However, not even in the flat case. So taking essentially taking a flat limit of the Bryan and Salomon manifold. So seeing as the Bryan and Salomon manifold as some kind of generalization of a flat space. So not even in the flat case, we can find tractable ODEs, and these are the work of Jason Lotte. So as we can't find integrable ODEs or nice enough ODEs to be studied, not even in the flat case, there is no hope to find something doable in the curved case. So the last SF reaction, so the last SP1, is not tractable. So this is all I wanted to say. Thank you very much for your attention. I hope you enjoyed the talk, and bye.